Okay, class, as we get into fundamentals of probability, I wanted to kind of, just like we ended the statistics topic, talking about probability distribution and how that relates to statistics, we're going to continue to talk about probability distribution and how that relates to um, from probability to statistics and statistics to probability. So to do that, I thought I'd take a look at a particular problem that's from your guys' homework. And here we have it. So there we go. Suppose that resting pulse rates among healthy adults are normally distributed with a mean of 72 beats per minute and a standard deviation of 16 beats per minute. So use this table or the ALEKS calculator, and I'm going to show both techniques to find the percentage of healthy adults who have a resting pulse rate that are more than 48 beats per minute. And then it tells you for your intermediate computations, use 4 or more decimal places. I would argue that that could give you an error and you should probably use 6 if you are doing intermediate steps. I'm going to try to avoid that and kind of show you techniques to not do that. But if you do that, please consider using 6. And partially because it's a decimal while we work with it, but we want the answer as a percentage, which means already 4 decimal places had to be saved. So only using those 4 could be a problem. So there's two things. Or the first thing I want to mention is that at this point, we know enough about the empirical rule that we might say, well, okay, is 48 a even standard deviation? Because then I could use properties of empirical data or the empirical rule, the 68, 95, 99.7 rule, that I could get there faster. So I say, okay, well, 72 minus 16 is 56. Minus 16 again is 40. Darn it. So I'm less than 2 standard deviations away from the mean, but greater than 1. So I need something else as a tool. And one of the things I had mentioned previously as a statistic was a z-score. And now we're going to actually get to use that. And it's not that complex, but there's quite a few different normalizing statistics, uh, z-score being one of the most basic. So we're going to start with that. First thing we need to do is we need to know how to compute the z-value. Well, the z-value is just the data that we're interested in, the data value minus the mean divided by our standard deviation. So for us, that means we have 48, we minus the mean of 72, and we divide by 16. Now, these can be positive or negative. This is not a probability yet. This is just the tool we use to find it. So if we're using the table, well, we want to do this first. We do the data value minus the mean divided by standard deviation. Then we get that value. So 48 minus 72 over 16 is negative 1.5. The next step is we pull up the table. And this table goes pretty far. I took out the piece we need. So let's look at that. So here's our table. And the tables are set up differently. This is one way that it's set up is to give you 2 decimal places, like you see here, negative 3.38, 0.32, and there's positive and negative values. And the one that we're interested in, some tables are not set up like this. Some tables have just the whole number and then just 1 decimal place, and then across the top it has the second decimal place. But it just depends on the table. Please be aware of the table you're using. This is the ALEKS table, so you're seeing exactly what you would get on ALEKS. And the one we're interested in is right there. So there's our negative 1.50 is 0.0668. Now, that being said, this says that we want to know the percentage of healthy adults who have a resting pulse rate that is more than 48 beats per minute. The thing with this Z value is it gives us everything from this value down. So this is giving us from 48 down. If I was to try to like a real quick sketch of this, I have, let's see if I can do this. I have my nice bell curve, assume it's nice. I have a middle, which in our case is the 72, right? That's this right there. And then we have this value over here. We're going to just put it right here. This is our 48. So this is the 48 that we're interested in. And what happened here is that this value, this right here, this value is giving me how much is less than. And it's going all the way, all the way, all the way. This is everything that's less than. So if I want to know how much is more than, so I don't really want less than, I want more than. Here's what I know. I know that all of this from wherever the end is to wherever the end is 100% of the data. Without a doubt, that's 100% of the data. Well, if this is this percent, this 0.0668 as a decimal, what's 100% as a decimal? Well, 100% as a decimal is just 1. 100% is equal to 1.00 as a decimal, or 1. Well, great. Knowing this, I could really just say 1 minus this would give me my answer. So that's what I do. I say 1 minus 0.068 is 0.9332. I convert this to a percentage, I would get 93.32%. Now I said I'd show you more than one way to do this. This is using the table. This is using this piece, right? That's hyperlinked, and you're more than welcome to use that. But the reality is you're not going to always have a table when you're out someplace. Yes, for the class, you'll always have a table, but the table's in the assignment. You don't always have a table. So one technique is to use the ALEKS calculator. Not every calculator can do this. Not every calculator has the ability to do this. But the ALEKS calculator is pretty robust and it has this ability. If I use this button right there, I can plug in the value of my Z, and I basically take this piece here, right? And I just, well, I plug that piece in. So I plugged in this. You do need to watch that you put parentheses or you hit the fraction button first. Could I have found this value? I could have plugged in this value. I could have found it first. But my goal here is to show you a time-saving technique. That way, if you get this question on the exam, you're not taking all of this process. You're not doing this piece, 1, and then this piece, which is 2, and then this piece, which is 3. And then 4, you round it, right? You're not doing that. You're doing one piece, you're going to the calculator. In this case, you needed to know that you were doing 1 minus, which we could read and we would know that from the question. This is why reading these questions are vital. So I put in the 1 minus first, then I hit my button here, And then it gives me, when I hit enter, it's going to give me this answer right here. And then I would still need, so plugging it in is one step. I guess hitting enter might be step 2, but that's a pretty easy step 2. Much easier than looking it up on a table. And then you're at 3, you're rounding. So it could save you time. And that's my hope. So this is one of the things I wanted to come over, but we're going to continue this talk about probability, and we're going to continue this process. So let's talk about some definitions. First, outcomes are the most basic possible result of observation or experiment. This could be something like, if I'm flipping a coin, I get either heads or tails. So my outcomes are heads, tails. We usually denote them as a set, so we would do curly brackets, heads, comma, tails, curly bracket. So that's how we would list it. That is the outcomes, and it's all of the outcomes. You always, when we talk about this, or as a sample space, we talk about it, and we're listing all of our outcomes. Now, the other thing is an event. The event is what you're interested in. This has one or more outcomes that share the property of interest. So how we say it's what you're interested in, what the question is asking. On a 6-sided dice, I would have outcomes of 1, 2, 3, 4, 5, or 6. If I was interested in when those are odd, well, I would say, well, that happens 1, 3, and 5. So then I could talk probability by saying the outcomes I'm interested in, the event, over my total outcomes is actually what probability is. And so we're going to, first, we need to be able to determine what are our outcomes and what are our events. So to do that, here's an example. We have a bag, has 6 balls labeled A, B, C, D, E, F. One ball is randomly picked and its letter will be recorded as the outcome. Give the sample space describing all possible outcomes. Then give all the outcomes for the event of choosing a letter from D to F. Sorry. So first, my sample space. My sample space could be any of the 6 balls. So I would put a curly bracket A, comma B, comma C, comma D, comma E, comma F. Curly bracket. The event I'm interested in is the letters between D and F, including D and F. So I would do a curly bracket D, comma E, comma F. So I would have this as my sample space or my outcomes, and this as my event. If I wanted to figure out this probability, I would put this over this, and that would be 3 over 6, or 1/2, right? I should mention that with probability, there's this weird habit that we have of either writing it as a fraction, 3/6, 1/2. We always simplify, right? In probability, you always simplify. Or we write it as a decimal, 0.50, right? That's what this is. Or we write it as a percent, 50%. So you have to read the directions to figure out which one it's asking about. There's something closely related to probability, and that is odds. Odds is the event that you're interested in versus the opposite of that event. So, like the odds of winning a game would be all the events that were successful against unsuccessful. And odds is never simplified because it's not a true fraction. Even though sometimes some people tend to write it like a fraction, it is not a fraction. So we do not simplify odds. I don't think there's an odds question in here, but just so we can differentiate that. Some other aspects. One, probability is either certain, it's anywhere between certain and impossible. So the probability of 0 means an event is impossible. It cannot happen, okay? If the probability I'm going to get heads by rolling a six-sided dice, well, I'm rolling a six-sided dice. It has sides 1, 2, 3, 4, 5, 6. At no point does it have heads. I'm not getting heads rolling a six-sided dice. So that has a probability of 0. It means it's impossible. By the same token, if I'm flipping a two-headed coin, the probability I'm going to get heads is certain. So that has a 1. And everything else is a measure of likelihood. How likely we are to have something happen. The traditional halfway example, it tends to be 50%. So 50% of flipping a coin, right? We flip a coin, it would then go to heads or tails. 50%, if it's a fair coin, 50% it's going to be heads, 50% it's going to be tails. So this is just a common way to talk about it. A bag, here's your try. So yes, I'm not going to go over this, but this is a try that would happen in the classroom and or did happen in the classroom, depends on the class you're in. And you guys can try it on your own. So theoretical method for equally likely outcomes. So there's different types of probability. And the first one we're going to talk about is theoretical, because that's kind of where we started. When we were talking about the flipping a fair coin, theoretical says it's going to be 50%. But the reality is, if I flip a coin 10 times, it doesn't mean I get 5 heads, 5 tails. It's not necessarily 50%. If I did it 100 times, I'd get closer to 50. 1,000 times, I'd get even closer to 50. 1,000,000 times, and I'd be real close to 50. But I wouldn't necessarily have hit 50. I may not be exactly at 50%. So the way it works is we count the total number of possible outcomes, and among all the possible outcomes, we count the number of ways the event of interest can occur, and that determines our probability. So let's try this in example. Let's start here. So assuming that there is an equal chance of having a boy or girl at birth, what is the probability of having 2 girls and 2 boys in a family of 4 children? I shared in class, it's not really 50%, but it's fairly close. So we're going to go ahead and use that example. We're going to say it's equal. So here's the probability. Here's the possible combinations or the sample space. I could have all 4 girls. I could have 3 girls and a boy. I could have 2 girls, a boy, and a girl, and so on, listing every possible way I could have these children, 4 children. And I list all the girls, and then I do 3 girls and 1 boy, 2 girls and 2 boys, 1 girl and 3 boys, and all 4 boys. And if we sum all of this up, how many ways are there? There's 1 way here, so this is 1. This is 2, 3, 4, 5, 6, 7, etc. There should be 16 different ways. And then we say, okay, how many of them were 2 boys and 2 girls, or 2 girls and 2 boys? So there's 1, 2, 3, 4, 5, 6. So I have 6 out of 16. Well, 6 out of 16 is 0.375. So as a decimal, as a fraction, it would actually be, it would be 3/8, because we would simplify that, so 3/8, or it would be 0.375. So that's the probability. And this is theoretical. Again, in practice, it would take a lot of children to determine how close we could get. And at different times throughout history, there have been more girls born than boys. Currently, I think in the US, boys are at 51 something percent. You're 51% more likely to have a boy than you are a girl. It's not huge in any way, shape, or form, but it's close. And it's been that way for a while. And then the probability of an event not occurring, if the probability of an event A is P of A, then the probability that the event A does not occur is 1 minus P of A. We've kind of already seen this work, and we're going to kind of play with an example, a little bit of one. Now, actually, I'm going to take the previous example. Let's do that. Since the probability of a family of 4 children having 2 girls and 2 boys is 0.375, or 37.5%, what's the probability of a family of 4 not having 2 boys and 2 girls? Well, if I wanted to know what the probability of not having, I would go ahead and say not 2 girls. That means it's not going to have 2 boys. So, and that would be 1 minus 0.375, which is 0.625, or 62.5%. Let's try another example using both of these. So first we'll start with this. A bag with 6 marbles shown to the right. 3 marbles are red, 1 is yellow, and 2 are blue. A marble is chosen from the bag at random. What is the probability that it is red? And what is the probability that it is not yellow? Well, the probability that it's red, since there are 6 marbles and 3 of them are red, well, each marble has an equal chance. So we would have the following. Number of red marbles over total number of marbles, 3/6 is going to be equal to 1/2, or 50%. Now, I want to know not yellow. So there are 6 marbles. 1 of them is yellow. Now, in this case, I could count the other ones, right? It doesn't feel crazy. But if there were thousands of these, I wouldn't want to count them. I'd want to have this technique in my toolbox to solve this. So that's kind of what we're doing. So the probability of not choosing a yellow marble is 1 minus the probability of choosing a yellow marble. So I do 1 minus the number of yellow marbles over the total number of marbles, which is 1 minus 1/6 is equal to 5/6. And again, this is using theoretical probability. We're going to talk a little bit about some other types of probability. So first, an empirical probability. This is based on observations or experiments, and it's a relative frequency of the events of interest. It is also often misconstrued or miscalled experimental probability. Actually, there's nothing really wrong with that, but it makes it sound like probability isn't a studied process. It's an experiment. It's not. So empirical probability is a little bit better name, but oftentimes people call it experimental. And then we have subjective probability. That's an estimation based on experiences or intuitions. We've all done this. In fact, subjective probability is how most people use probability. This could be something like choosing what lane of traffic to get in, because you're hoping it's the lane that's flowing best, or what line at the grocery store to go in. So these are subjective probabilities, and they should improve with more experience. Just like empirical probability should improve with more experiments, subjective probability should improve with more experience. That being said, I'd love to say that's the case, but some people don't quite learn from stuff. Let's see this happen. Here's the three types, and this is kind of how they're related and intertwined. So theoretical probability, the chance of rolling a 4 is 1 out of 6, or 1/6. That's theoretical. That's theoretical. Empirical, she's a 92% free throw shooter for the season. So I'm taking how many times she's been successful through this experiment or through the data of her free throws, and saying that 92% of the time she makes it. And then subjective, there's about a 70% chance she will go out on a date with me. So again, that's the subjective, that's the one we use the most, and we often don't think about how we develop it, but we do develop it, hopefully. So let's compare these. So we have this spinner. Again, these problems are just taken directly from the homework. So the spinner shows 10 equally sized slices, and Anne spun it 25 times and got the following results. She got these results. So you need this information for one of these, A or B, depending upon which one's worded first. And then you need this for the other piece. Wow, that's tougher than I thought. So you would need the spinner. So there'll be two things. It won't always be a spinner. Sometimes it's just a box of data and it's rolling a dice or picking a number or something. So from Anne's results, compute the experimental probability of landing on gray. Well, I see that gray happened 11 times. And I know she did this 25 times. That means 11 over 25. And depending upon how they wanted the answer, I could make that a decimal if I needed to. Assuming that the spinner is fair, compute the theoretical probability of landing on gray. Well, it's assuming it's fair and they're equally sized slices. I have 1, 2, 3, 4 gray. I know that there's 10 pieces. It tells me that there. So I take these 4 and I say, well, that's 4/10. And if I had to convert this to a decimal, this one I can do, because 4/10 is 4/10. 4/10. Now, the question asks, assuming that the spinner is fair, choose the statement below that is true. The experimental and theoretical probabilities must always be equal. They're not usually equal. Okay, rarely is that the case. So you're not going to see that. The next one is there will be, as the number of spins increase, we expect the experimental and theoretical probabilities to become closer, though they might not be equal. And or the other one says, as the numbers of spins increase, we expect the experimental and theoretical probabilities to become farther apart. So these are worded very challenging. So they're not always worded this nicely. Sometimes they're worded saying, do you expect the data, if with a fewer number of spins, do you expect the data to be, let's see, do you expect the data to be closer or farther apart, or less than or greater than, and that sort of stuff. So you do need to be careful that you're reading these very carefully. They are sometimes challenging. In this case, as the number of spins increase, this means the experiment here has gone on more than just 25 times. Maybe she did it another 25 and another 25. So as it increases, we expect the experimental and theoretical probabilities to become closer. They may not ever actually reach, but they can become closer. So that's kind of what we expect. And I kind of walk through, I'm just going to go ahead and do that here so we have that. And then on this next slide, you'll see I walk through each one of these pieces. I'm not going to read through them again for you, but we've already walked through them, but this is the meat of this. Again, for A in this case was the experiment. So we looked at the experiment and we got 0.44. B, we don't look at the data at all. We just look at the theory. We got 0.40 or 0.40, and then I give you more meat to the argument on this. All right. So this is, I think the next piece was the last try for the day. So my hope is some of this helps, and you can see how these are written a little differently. Give the tries a shot, just see how you're doing, see if you understand the material. Otherwise, I will see everyone next week after Easter. Have a wonderful weekend.